Okay, so now we're going to do example 6.3, which is an actual beam design. So what we've done is analyze beams that have been given to us. We do that a lot in the design classes, but actual design means you're going to have to pick the section type. So I'm going to go through this one fairly quickly because we've done several versions of examples and notes on this, but take it from top to bottom beam design. You may need to pause the video and go look up stuff in the tables as we go, because I'm not going to stop and do that for each of the coefficients this time, or the modifiers. All right, so we are going to design a roof beam. So we're going to design roof beam. And just basics here, it's got a uniform load, dead load, live load, and then it'll have self-weight. It is a span of 13.5 feet. And it is, the beams are at 16 feet on center. No ponding, so we've got a sloped roof. Oops, sorry. Let me back that up. So you don't have to worry about that. Ceiling is gypsum wallboard. We have plywood sheathing. So no lateral buckling. And we're going to use a number 1 Douglas fir L. I think that's large. The moisture content is less than 19%, which is what we're always assuming for structural purposes. And normal temperature conditions apply. Normal temp. Dead load is 14 pounds per square foot. Live load, roof load is 20 pounds per square foot. And we're going to find a section based on flexure, check for shear and deflection. Design for flexure. Then we're going to check shear. We're going to check to make sure deflection limits are met. And the limits that we're going to use for deflection are live load deflection. Max is going to be L over 240. And total load deflection max is going to be L over 180. All right, so that is our plan for this beam design. Okay, so now that we know what the problem layout is, I'm going to move into the design. All right, so I'm just going to write our little beam up here again so we can refer to it. 13.5 feet, and I think I've got everything there. Okay, so W dead load, 14 pounds per square foot, 1.33 feet. Where does that come from? That's the on-center spacing, 18.67 pounds per linear foot. Live load, 20 pounds per square foot times the 16-inch spacing was 26.67 pounds per linear foot. So our total load is 45.33 pounds per linear foot. So remember, we aren't factoring loads, right? So you're probably used to that by now, but just a reminder, since I work in concrete most and steel next most, I have to remind myself that not to factor these loads when I'm working on wood design. Okay, so let's start with flexure bending. Moment equals WL squared over 8. Our total load is 45.33 L squared over 8. And our moment is 1033 pound-feet. So our bending stress FB prime is equal to the F sub B times each of the factors we need to consider: CD, CM, CT, CL, CF, CFU, CI, CR. Now we've gone through these enough times that I'm going to go ahead and just give these to you, or write these down. You need to go check them. C sub D. And the best table to look if you forget what things are is that table 4.3.1 in the actual NDS. That's the table that tells you, so for instance, for bending, that we use all these factors, but it also defines what the factors are. So CD is the load duration factor. Use 1.25. See the commentary in the NDS, L sub R. C sub M is 1. C sub T equals 1. C sub L equals 1. That's braced. That's the lateral one, and that's braced by plywood. C sub F. So this is the size factor modification. So at this point, we don't know exactly what the size is. So this is just a starting guess. Once we know what size, we can refine this and check it. So you may, flag that or something so that you go back and check it. C sub FU equals 1. C sub R equals 1.15. And so we also look up F sub B for this type of wood and in the supplement, and that's 1000 psi. So our F sub B prime equals 1725 psi. Okay, so our required, so now if we look at our equation, M equals F sub B prime over S. Okay, I know these other two now. I need to solve for S, right? So this M value that we have from the loads is what's required of us. F sub B prime is what we have. And so whatever I get for S is going to be the S minimum that's required. So anything bigger than this S should work for flexure. M over F sub B prime. The moment is 1033 pound-feet. Do a unit conversion here. Divided by 1725 psi. Gosh darn it. 1725 psi. And our S required equals 7.18 inches cubed. Okay, so we have to find a section that's going to work for. If we go into table 1B of the supplement, gosh, okay, 1B of the supplement, we can look at dimension lumber. Let's do, you can look at the table, pick some different things. If I look down that table, one of the things that works here is a 2x6. And of course, we're looking at the S sub SX. So 2x6, for instance, has an S sub XX of 7.56 inches squared, which is greater than 7.18. I'm sorry, inches to the third. It's greater than 7.18, but it's not crazy bigger than 7.18. So this should be okay. We need to check a couple things. So remember that C sub F is, we have to check that for 2x6. And I get a C sub F equals 1.3. It's actually greater than 1.2, so it's okay. I could go back in and recalculate S required and see if I can get a little bit lower value, but we're pretty close here. So I suspect this is either the most economical section or pretty darn close, and it passes. So now let's just see what we're actually providing here as a final check. Stress M over S equals 1640 psi. Hang on just a second. F sub B prime. We can actually go back and figure out with the new factor. 1.3 over 1.2 equals 1869 psi. And little f sub b is less than f sub b prime. So we're okay for bending. Okay. We also should check this with self-weight. I'm going to go ahead and look at shear first, but I'll go ahead. We should probably check it for flexure first. Okay, so okay for bending. Add self-weight and check. So you can do that adding of self-weight anywhere along here. This is kind of just a check to see if we're in the ballpark. So check with self-weight added. We get for our 2x6 number 1 df-L, we get a density from the tables or from the equation of 62.4 G over 1 plus G 0.029 times the moisture content. This is the equation. 1 plus moisture content over 100. We get a G equals 0.5 for Douglas fir larch, and we know our moisture content is 19%. So density here comes out to 34.2 pounds per cubic foot. Call it 35. So, or we'll use the 35 from the table. 35 pounds per cubic foot, and we get 2.005 pounds per linear foot. If this is not making sense, go back through one of our previous problems where we work through this process. So now my moment is equal to the 45.33 plus the 2.005 pounds per cubic foot, 13.5 foot squared over 8. And now my new moment is 1078. So this is why, so if I was doing a concrete beam, dead load is a huge part of it, right? On these wood beams, they're pretty lightweight for what we're doing here. So I've added in 2 compared to the 45 I already had, and I was pretty good on stress, so this shouldn't be an issue. Whereas in a concrete beam, we go ahead and try to get an estimate of that in right away and check that right away with dead load. All right, so little f sub b is m over s. In this case, I'm going to get 1711 psi, and that is still less than the 1869. So okay for bending. All right, so at this point, we're just going to check shear and make sure we can meet our deflection limits. Just a sec. All right, shear. And I actually originally did this with the shear ahead of time, so W total load, but we need to add in plus dead load, and that ended up being I'm going to have to do a little bit of this on the fly here. So I think what I'm going to do is, because I originally did this first through without dead load and added it. Okay, so let's do shear next. I'm going to stop this. This will be a short video with just the flexure, and then I'm going to pick this back up and we'll do the shear and deflection check.